Hello again. Let's now continue with the three-phase induction motor. The induction motor is of course exposed to a traction load, which we discussed before. It's a large load range and it's a varying speed. And it's typically also a varying frequency and varying voltage applied to the motor because of what we'll see later on, the typical way to control the machine. The power supply is not sinusoidal. It's typically a pulse width modulated three-phase voltage applied, which means that we'll have a lot of harmonics. And in comparison to industrial motors, there is no real startup sequence in the way it's done for industrial motors, especially those who are operating at fixed frequency. A few pictures of induction motor. This is not pictures that show a typical traction motor, but they show you a little bit of the design and how they are built up. This is a stator core. Well, inside you have a complete rotor, and you can see the stator is built up of thin iron sheets stacked like a pancake with slots in it on the circumference of the stator inside, and the stator inner surface. And you can see here that we have the windings coming out of the slots, and this part here is referred to as the end windings. That is, depending on the pole number we have, if it's a 2-pole or 4-pole machine, this winding will have different shapes. A 2-pole motor, typically the conductors coming out of this slot will have to go around 180 degrees and back on the back side of the motor to the other side, and then again come up to this slot. If you have a 2-pole machine, that generates quite a lot of copper winding to so to say make the winding a complete turn, and that builds pretty long end windings for low pole pair numbers or pole numbers. If you have a higher pole number like 4 or 6, it means that the winding has to just, instead of having 180 degree pitch, the pitch will be only 90 degrees or 60 degrees, and thus we have less copper end windings and shorter end windings, which is a way of analyzing what kind of winding there is in a typical stator, if you know this. I would say this is probably a 2-pole motor. I'm not really sure. Can be a 4-pole motor as well. This shows the different parts of the machine. I'm sorry, the text is in Swedish, but I will show what it is. This is a rotor, and with this, it has a squirrel cage rotor or a cage winding. That is, it's not a winding itself. It's like a cage built up of aluminium or copper. So it's a cage, and then they have short circuit rings on each side. This rotor is then, of course, put into a stack of iron sheets in the same way as the stator, with the slots for this cage winding. There are different kinds of rotors for induction machines, but typically for induction motors, for trains, it's cage windings. This is the stator mounted in a housing, and you can see the slots here. And this rotor is, of course, mounted inside the stator with the bearing shields on each side, this side and that side. And this industrial motor has a typical fan at one end here. This shows a photo of a machine which is broken up, and you can see the rotor here, and these small traces you see here, that's what you can see of the slots inside the rotor. The most part of the winding is inside the rotor. You cannot see it, but you can see a little bit of the slot, the opening of the slot in this case. The air gap is here in between the stator and the rotor, and the stator, of course, it's here. It's pretty black there, so you cannot see it very good. So let's now look a little bit into the operation of a three-phase induction motor. This is a principal sketch of a three-phase induction motor, and it shows a few of its features. First, a three-phase stator with three-phase windings. That is, we have 3 windings in the stator, and they are distributed in space with a phase shift 120 degrees between each other. So this is a mechanical angle in between. This is the magnetic axis for the A phase, and the B phase is lagging the A phase by 120 degrees. So it's very important to remember that the winding, three-phase winding in the stator is distributed in space in the machine. This circle shows just a simple sketch of the rotor itself with a short circuit cage winding. So what are the fundamental requirements to make this motor work? Well, the first one is, as I mentioned, a three-phase winding distributed in space with a shift of 120 degrees. That is what we saw here with the three-phase windings in the stator. Secondly, when we apply a voltage, a three-phase voltage that is phase shifted in time, as you can see here. So we have a three-phase winding in the stator distributed in space, fed with a three-phase voltage that is distributed in time. So one distribution in space and one in time. And that leads us to a sinusoidally distributed rotary field in the air gap. That is, we have a winding, we have a field or a magnetic flux that rotates in the air gap. And that is, of course, not exactly sinusoidal, but it's a pretty good sinusoidal signal that varies around in the air gap. That speed of this sinusoidally distributed field is determined by the frequency of the applied voltage. Let's assume it's a two-pole machine. If we apply 50 Hertz as the frequency of the voltage, the rotor field will rotate with 50 revolutions per second. So the frequency directly determines the speed of the rotating field. And of course, if there's a pole pair number different from 1, let's say it's 2, that means 4 poles, then of course the rotation, the synchronous speed will be half of that one for a two-pole machine. So obviously we have a rotating field with synchronous speed in the air gap. So let's now look at the rotor. If the rotor initially stands still, it means that we have a time-varying field rotating in the air gap along the rotor surface. That means that the flux linked to the rotor will be a time-varying flux. And that means that there will be voltages induced in the cage winding due to this time-varying flux. And if there are voltages induced in the cage winding, there will also be currents since the cage winding itself is short-circuited. That is, this is the basic principle of the induction motor. That is, that there is a time-varying flux linked to the rotor that induces voltages and currents in the cage winding, that in turn interacts with the rotating field in the air gap to produce a torque on the rotor. So the rotor will start to rotate with a speed n, for instance. So let's now once again assume that we are looking from the rotor into the air gap and the speed of the rotating flux. That is, now the rotating flux will, relative to the rotor, rotate with a lower frequency because they will have about the same speed at normal operation. Let's assume that we have n equal to ns. That is, the speed of the rotor is equal to the synchronous speed of the machine. In such a case, it means that if you're looking from the rotor to the air gap, you will see the same value all the time of the air gap flux, of the rotating air gap flux. That is, there will be no time derivative referred to the rotor itself. The flux linked with the rotor will be a DC, or a constant value. That is, the time derivative will be 0, and thus there will be no voltage induced, no currents induced, and no torque produced. So that is quite interesting. This is why you sometimes refer to the induction motor as asynchronous motor, because it cannot produce a torque when it operates synchronously. It has to operate asynchronously to produce a torque. that was a little bit of the basic physics behind the torque production in the induction motor. Pretty popularly described, but I think that's a good, useful model to have if you're not going into the very details of the motor. If you look now at the sketch again and the speed of the air gap flux and the speed of the rotor, we can define a few important parameters. The first one is the slip, and that is a relative measure of the difference between the rotating, the synchronously rotating flux and the speed of the rotor. In the rotor, the frequency induced will be the slip times the applied frequency, the stated frequency. That is, if you have a stated frequency of 50 Hertz, and if you have a slip of 5%, you will have a 2.5 Hertz frequency of the AC induced in the rotor. And the rotor speed will be determined by the slip and the synchronous speed. So let's assume we have a slip of 5%, then of course the speed of the rotor will be 95% of the synchronous speed. And the synchronous speed itself is determined by the frequency of the stator voltage divided by the pole pair number. This is a pole pair number in this case, so one means a two-pole machine and so on. That was end of part 2.